So today's video is going to focus on describing your quantitative data here using numbers now, instead of just words as we describe these graphs. So let's focus first on center. There are going to be two ways that we are going to focus on measuring center and quantifying center via mean and median. So let's look at mean first. Mean is exactly what it has always been, right? Mean is what most people call your average. Right, so you're going to use the notation that you will use for it is X bar, and it might be a little hard to see. It is literally X with a bar over it, and it is pronounced X bar. And we are going to find mean just like you've always found mean, right? Add up all your data points, divide it by your sample size. Again, don't get caught up in a weird looking formula for something that you already know how to do. So go ahead, pause, take a second, and do this example here. Okay, so when working with this example, you had to hopefully remember how to read the stem plot. So for instance, the first one is 5 plus 10 plus 10. When you're doing long problems like this, you don't need to write everything out. After the first 2 or 3 points, you can then put 3 dots, another plus sign, and then just list that last point there. And it was over 15 North Carolinians divided by 15, and go ahead and get your answer here of 22.5 minutes. Okay, so that would be a way that that would still count as fully showing your work if you were asked to show your work by listing it like that. The second part here asked you to calculate the mean again, but excluding the 60 minutes. So again, you could show your work the same way, the 3 dots, but this time my last value here would be 40, and I'm dividing by 14 instead of by 15. So now my mean is going to change a little bit. Now I'm going to get 19.8 minutes. So one of the things that you hopefully noticed here and saw here is that the two values were different. And that by excluding this one very high value here of 60, that I had a decent sized swing in my mean. And so we need to understand that mean is what's called not resistant. So mean is going to be influenced by outliers or by points that are pretty far distant from the rest of our data set. Here, our next one is median. Median is going to be important when we're looking for a midpoint. Right, so median, we are going to need to first arrange all of our numbers in order from size, from smallest to largest. I can show you how to do that on your calculator if you don't already know how to do that once you've put your numbers into a list. Remember, if our data set has an odd number of values, let's say there's 11 pieces of data in the data, then the number that is in the center is our median. If our sample set has an even number of samples, let's say there's 12, then I'm going to average my 2 center observations. So pause for a second, go ahead and try to complete this sample problem. Okay, so for the first part of this one, it asks to find the median travel time for our 15 North Carolina workers. Well, that's an odd data set, so I can just literally find the one that's in the middle. I put them in order. There are 7 pieces of data on this side, 7 pieces of data on this side. Therefore, 20 is what is in the middle, and that is my median. The second one, stuck in traffic here, asks you to make a stem plot of the data and be sure to include a key. So we have to do a key to define what you're talking about. So our key here, 30, is a New York worker that reported a 30-minute, you should probably say 2 work travel time. And then I'm going to find my median by hand. So when I'm finding my median here, if I make a stem plot, I've already put them in order here, right? I have 20 randomly chosen New Yorkers. So I need to find my center piece, my center 2 pieces of data, because this is an even data set, and I need to average them. 3, 4, 5, 6, 7, 8, 9, 10. Okay, so there are 9 pieces of data in front of here, then 1, 2, 3, 4, 5, 6, 7, 8, 9 pieces after. So these are my center ones. So I have 20 plus 25. So if I want to average those together, I can get my median New York travel time at 22.5 minutes. And another way that median will differ from our mean is that median is resistant to outliers. You'll notice on our stem plot here, we have a 85 out here kind of by itself. That doesn't change the median of 22.5. The 20 and the 25 are still the two pieces of data that are located there in the middle. So mean is going to be resistant to outliers or influential points that could potentially change the value of a mean. Okay, so when we compare the two, if we look in our information box here, mean and median of a roughly symmetrical distribution are close together. So essentially, if I have a roughly symmetrical distribution here, I should have a mean in the middle, and my median should also be in the middle. Now, if my data is a skewed distribution, so let's say I have a right skewed distribution here, my median will be closer to the peak, and my mean will be further down the tail. Because remember, mean is going to be the value of the mean is going to be affected by these data points that are way out here where the median wouldn't. So if I had a left skewed piece of data, again, my median would be a higher value here because it would be more in the peak, and my mean would be further down the tail because, again, the mean is going to not be resistant where the median is. Okay, take a second, pause, go ahead and try these examples, and we'll check your answers. Okay, so when you're looking at these, so this is based off the New Yorkers from before. So we know the median at 22.5 minutes. Based on our stem plot, would I expect the mean to be less than, about the same, or larger than the median? Well, based on this stem plot, if I look at how my data is distributed here, right, I have a form of right skew with my data. So my median is going to be here, and my mean will be further down the tail. So I expect my mean to be larger than the median because it is in the Y is because the data has. Go ahead and find the mean. Hopefully you found a mean travel time of 31.25. So as we said before, the mean is definitely going to be affected by these higher numbers here. So would the mean or median be an appropriate summary for the center of distribution for this one? For this, when data is skewed, median is usually our better choice here because our justification is here because the distribution of the data is skewed. Okay, so let's look at how we can calculate spread now that we've calculated center. So one of the ways that we can calculate spread is using quartiles and our interquartile range. We can also use standard deviation to calculate spread. We will use, the one we will use will depend upon which measure of center that we are using. So let's start first here with quartiles. So quartiles, the first thing we're going to do is we're going to put our observations in increasing order. And you'll notice we're using the median. So we mark and locate the median. You can see we've done that down here with our example of our 15 North Carolina worker travel times. So the median there is 20. The first quartile is going to be the median on the left. So I have 7 values here on the left. Okay, the median value on the left is going to be 10. That's going to mark my Q1. The third quartile is going to be the median of the values on the right. I have 7 values on the right. The median of there is 30. So I have a Q1, the median, which essentially would be Q2, and then Q3, which is my third quartile. Okay, and then I can use those to calculate my IQR. IQR is my interquartile range. It is my Q3 minus my Q1. So for this example here, my IQR would be 20 minutes. My Q3 subtracted from my Q1 subtracted from my Q3. Okay, so back to our New York example. Go ahead and pause it. Take a second, see if you can determine the IQR as well as interpret it, and we'll check your answer. Okay, so if you remember from these before, our median was 22.5. Our median was located right here between these two values. So this example is a little bit different because I have an even number of values now. I have 20 data points instead of 15. So when I'm looking at all of my points to the left here, I have to include that 20. And when I look at all of these points to the right here, I include that 25. So when I look for my Q1 is going to fall here between these two 15s here. It's going to fall right between there. So my Q1 would be 15. Right, because I have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So 15, 15. I get 15. 2, 3, 4, 5. Over here on the right side, my Q3 is going to fall here between this 40 and 45. So my Q3 is going to be equal to 42.5 minutes. So now when I go find my IQR, I need to subtract the 15 from the 42.5 minutes, giving me a total value of 27.5 minutes for my IQR value. So what this means, when we're asked to interpret it here, we need to explain what it means. So our interpretation here is that the range, remember, is going to be a one number value. Range is not 15 to 42.5. The range is 27.5. So the range of the middle half of the data, that's what's happening here when we're looking at this IQR. We're looking at the middle of the data. Basically, we're looking at the data points. If we were looking at 100 data points, we're looking at the data points between 25 and 75. So the range of the middle half of, and we have to use our context because we love our context in stats. The middle half of travel times for the New York workers is in the sample. Officially, it would be in the sample because we only looked at these 20. We didn't look at every possible New York worker. Is 27.5 minutes. So using our context, using our units, being very specific here at what it is we're looking at. Okay, so before we were looking at data, we would say things like there's a possible outlier or there's a potential outlier. We can now use this IQR to help us calculate whether something is actually an outlier or not. Okay, and so our formula for doing that is taking 1.5 times the IQR and adding it to the third quartile and subtracting it from the first quartile. So what we mean by this is that anything that would be an outlier is going to have a value less than whatever your Q1 is minus 1.5 times your IQR, or a value greater than Q3 plus 1.5 times your IQR. Anything, I should say less than, anything less than that or greater than Q3 plus 1.5 times IQR would be considered an outlier. So looking at your North Carolina example, we can try to determine if this 60-minute sample, if that one traveler that had 60 minutes, whether that is considered an outlier or not. So to do that, I'm going to go ahead and I'm going to calculate my 1.5 times my IQR, and I'm going to add it to my Q3. So I can subtract it from Q1, but we're only looking on the high side here. Right? So when we look at this, just a quick reminder of what our Q1 was, as well as what our Q3 is for this particular sample. Okay, so Q1 was 10 and Q3 was 30. And in this example, our IQR, remember, was 20, I believe. So when we are doing this, if I'm calculating for outliers, I'm going to say Q1 minus 1.5 times my IQR. So 10 minus 1.5 times 20. So that is going to give us a value of -20. And then on the high end, an outlier on the high end would be my Q3 value plus 1.5 times 20, which will give us 60. So any value greater than 60 would be considered an outlier. Any value greater or less than -20 would be considered an outlier. Okay, you'll notice when we look up here, it does not say greater than or equal to, it just says greater than. It just says less than. So 60 is right on the cusp. It's almost an outlier, but it is not an outlier. It is not quite big enough to be an outlier. So quantitatively, we can describe our distribution using what's called our 5-number summary. So the 5-number summary is going to consist of the smallest observation, so our minimum, the first quartile or Q1, the median Q3, and then our largest or our max. And we're going to write it in order from smallest to largest. So we're always going to write it in this order here. Minimum Q1, median Q3, maximum. Okay, we can also use our 5-number summary to build a box plot. Okay, sometimes it's called a box and whisker plot. You may have seen these before. Let me just kind of give you a quick sketch of what one looks like, right? Let's go long, let's go short here. Okay, so, and let's put here. Right, so this would be an example of a box and whisker plot. So when we're drawing this, okay, the edge of our box here, the left edge of our box marks Q1. The right edge here marks Q3. When you draw these, you're going to have an x-axis with values on it down here, right? So we're going to actually graph it in the right spot, right? So there's our x-axis there. So Q1 marks the left edge of the box. Q3 marks the right edge. The line in the middle here, this would be our median. Okay, and then the lines, or what are the whiskers? These are going to the smallest observations and the largest observations that are not outliers. So that's key. We need to understand how that can look a little bit different. Let's add to this box and whisker plot here. Let's add a little asterisk out here. Okay, so what that means is that this value out here, and there could be a couple of them. Let's put 2 of them out here. These values out here are outliers. This was not necessarily our minimum. This is our smallest value that is not, I repeat, an outlier. So you need to calculate your outliers to be able to do an appropriate box plot. Now this one right here on the far right, this end over here, that one is my maximum because I don't have any asterisks out past it. I don't have any outliers that are larger than it. So that is my largest observation, and it's not an outlier. Okay, so you need to pay attention to that. Again, when you are creating the box plot, you need to calculate your outliers, and your outliers are marked by these special symbols. They are not included in the line, nor are they marked by the whisker. So go ahead and take a second and see if you can sketch this box plot here with Barry Bonds. Okay, so to construct your box plot, you hopefully went through and you set up your numbers, right? We have our 5-number summary with 16 being our minimum. I'm actually not sure you guys can see. Okay, so with 16 being our minimum, 25.1 being our Q1, our median being 34, 45 being Q3. Our IQR is 19.5. Okay, checking for outliers, anything less than -3.75. So I don't think you need negative home run. Or anything greater than 74.25 would be considered an outlier. So in looking at this data set, I don't have any outliers in this data set. So on my box plot, I wouldn't have any special numbers. So when I would set up my box plot here, I would have my home runs on this x-axis here. So I would set up my appropriate scale here, and then I would go ahead and construct my plot. So my Q1 is at 25.5. My median is at 32. My scale here is by twos. My median is at 32 here. My Q3 is at 45. Right, so that makes up my actual box, the edges of my box and the line in the middle of my box. Okay, my highest value is a 73. It is not an outlier, so I don't need any special symbols or anything. I'm pretty sure you can't see what goes past the gray line. So I'm going to go ahead and stop it earlier than I should, but I think if it goes past the gray line on my side, you can't see it. And then my minimum is not an outlier either, so I go down to my minimum of 16, and my box plot is all set. You may also see box plots turned on their side like this. You could compare these, you could do this either way. They could be on their side like this, which is how I feel like we see them sometimes, okay, and then kind of just stacked on top of one another. And sometimes they'll be turned up and down and stacked side by side. Okay, so again, looking at these, you can see how this data plot does have an outlier. Okay, this is my highest value that's not an outlier. I don't have any outliers in that North Carolina data set, either low ones or high ones for either one of them. And now I could compare these data sets. Box plots are good for this side-by-side distribution of data set. They don't show as much detail as maybe a histogram or a stem plot for like one particular set of data, but they're good for comparing them. For instance, in these sets of data, we could see that there's a large right tail here. We have a lot of values, including that outlier that would go down that tail to the right side. So both distributions have a much longer line on the right side. So we could notice that both of them are skewed to the right. We could use their median values to help discuss that skew. The fact that the distance from the median value to the upper tail is much further than the median value to the minimum value. We can make a general observation about overall how New York travel times seem to be longer than North Carolina travel times. The maximum is higher, the median is higher for the New York travel times. The quartile values for both of them, Q1 and Q3, are also both higher for New York. New York has a higher variable range. It has a larger IQR, okay? And I can notice that just by looking at the size of the box, right? So I have a little bit more variability there with a larger IQR. And the fact that New York has an outlier while North Carolina does not. So now I can start to use these numbers to be able to draw some comparisons between these different data sets. Okay, so let's shift over then to mean and looking at spread around the mean. So looking at standard deviation. So in a previous example, one that we didn't do, in a previous example in your book here, they calculated a mean number of pets and they found it to be 5. Okay, and so they put the data into the data plot here, or you can to the dot plot, and you can see how they're calling the mean here the balance point. Okay, so the mean is in the middle here, and that's going to be where our data values are balanced out. Okay, so data value 1 is 4 units below the mean, so its deviation is a -4, right? It's 4 units below the mean, it has a deviation of a -4. The data point of 7 is 2 units above the mean, so it has a deviation of 2. Right? And so these deviations around the mean here are going to be kind of the basis for calculating what we call our standard deviation and our variance. So if you look at all the deviations around the mean, you look at this table down here at the bottom here, okay, and we look at all these deviations from around the mean, you'll notice the deviations are going to add up to a sum of 0. And this is going to happen because that mean is that balance point. So if all my deviations add up to a sum of 0 for the data set, okay, that's not very helpful for calculating the spread around the mean. So what we will do then is we will square all those deviations. So we'll go ahead and when we square all those deviations and we add them up, Now we end up with a sum that's not equal to 0. So we added them all up, and we got a sum of 52. Okay, so if I take this sum of 52, I'm looking for basically my average distance that these data points are from the mean. So when I take an average of something, I divide it. However, when I'm using standard deviation, I divide by n minus 1. So in this case, I have 9 data points. So I would take my 52 and I would divide it by 8, which would give me 6.5. And this average here, okay, this is called my variance. So I got this variance, again, by finding all my deviations and squaring them, and then going ahead and adding them all up, right? I got a sum of 52 down here at the bottom, okay? And then I divided by n minus 1. So I took this, x bar squared. So I did that, okay? And that gave me my variance. But you need to remember, we squared all these. So if we put these in units, right? These deviations are in units, right? I'm 4 pets less than the mean right here. I'm 2 pets less than the mean. I'm 2 pets more than the mean. So if I squared all of those, now I'm 4 square pets bigger than the mean, right? And that doesn't work. We have to undo that squaring that we did. So now if I take my square root of my variance here, now I can get down to just pets. And that will give me my standard deviation, which is going to be my typical distance away from the mean. Okay, remember, again, our mean is our balance point. So in this case, my standard deviation would be about 2.55 pets. My average data point is about 2.55 pets away from the mean. Let's look at more examples and stuff of this. Okay, so first of all, let's look at this formula. This formula is borderline terrifying. Okay, remember, this formula is on your formula chart, it's on your formula sheet. And remember, if you have the data set, you can plug the data set into your calculator, and your calculator will spit out standard deviation for you. And I will show you how to do that. Okay, what you need to realize about these formulas is paying attention to what can happen if I manipulate this formula, right? So my standard deviation, again, is measuring my typical distance in the distribution from the mean. And I calculate my variance, and then I take my my square root of that variance. Okay. When I look at the formulas, right? When I look at these formulas, I notice that I'm dividing by my sample size. My sample size minus 1. But my sample size is still in my denominator. So if my sample size is in the bottom of my fraction, right? It's in the denominator of my fraction. So if I increase my sample size, then my standard deviation should go down, right? If I decrease my sample size, then my standard deviation will go up because it's in the denominator of my fraction. So that's just something that you need to keep in mind, that standard deviation can be affected by these things that are in its formula. Obviously, it can be affected by the values of the mean and the values of the data points, the distance these data points are from the mean, but your sample size is going to have an impact on your standard deviation as well. Okay, so a couple more things just kind of regarding standard deviation in general. When you put a sample set into your calculator and you pull up standard deviation, you're going to have a couple of options of standard deviation. Notation, you'll notice, is going to be very, very important in this class. The S of X, that's going to be your standard deviation of a sample. The sigma of X is going to be your standard deviation, assuming that what you put in your calculator, what you use to calculate, was your entire population. We are most often going to use this. We're not going to have data for the entire population. And so our focus is going to be S of X, which is going to be the standard deviation of the sample. Standard deviation does have units, like we just talked about with the pets, right? The pets were the units. The units for standard deviation are going to be the same as they are for your mean. Standard deviation is your is your form of spread that you're going to be using associated with mean. So like mean, it is not resistant, right? It will move and it will shift based upon, outliers or really high or really low values. Okay, and these values are all clustered together here, right? Standard deviation would most likely be small, right? But now I go add in 2 values way over here. Well, now my standard deviation is going to go up, right? So it is not resistant, same as mean was not resistant. Also, your standard deviation is always going to be greater than 0. So if you come across, if you do something and you calculate a negative standard deviation somehow and or a standard deviation that is equal to 0, you need to rethink that and revisit what you've done. Okay, so take a second and let's try to work through this example and then we will check your work. Okay, so looking at this quickly, it looks like your mean fell off the side here. So the first one, calculating our mean, it is going to be equal to 75, right? Adding them all up and then dividing by 5 because we had a sample size there of 5. Number 2 there, it asks you to make a table and show for each value the deviation from the mean and then squaring it from the mean. So our deviation, remember 67 minus 75, right? That's why I got a -1. Right, but 76 minus 75, that's why I get a +1. Summing them all up, I get a total of 0. So if I square all those deviations and sum them up, I get a total of 156, which I can then use to calculate my variance. My variance is divided by n minus 1. So I take that sum of all those deviations, right? My sum of my deviations squared, divide it by n minus 1. I get 39 inches squared. So to find the standard deviation, I need to take the square root of those 39 inches. Again, I think it's cut off. So you get 6.24. Now I'm back down to actual inches, not units that are inches squared. And then the last one here asks you to interpret it. We're going to get a handout soon of sentence stems that you will be able to access for these interpretation type questions, where you can just kind of fill in the gaps, fill in the holes based off of the context of the problem and what it is you're actually trying to interpret. So when we interpret something in this setting, that means using your context. So we're talking about the player's height, typically vary by about, and then we put our standard deviation value in there, 6.24 inches. From the mean height of 75 inches. You notice I'm using context and I'm using my units all throughout my interpretation. And then the last thing is just a quick reminder over which one to use. Okay, we've kind of hinted at this a little bit as we go through, but median and IQR are better for skewed and strong outliers because remember, again, they are resistant to those values that are either skewing that data or are a potentially outlier. Okay. Mean and standard deviation are much better for distributions that are reasonably symmetric here and don't have that kind of skew and don't have outliers. So when you're given a data set, if you're trying to choose, that's the things you'd be looking for. Is it skewed or does it have outliers? Okay, I'm going to use median IQR. Is it roughly symmetric without any outliers? I'm going to use mean and standard deviation. All right, we'll be doing bunches of examples of this kind of stuff in class.